Hey y'all, today we're going to look at how to calculate molar solubilities if we're given the KSP for an ionic compound. Let's go ahead and get started. Before we get going, let's talk about some of the terms that we're going to use in this video. The first one is remembering our equilibrium expression, which is KSP is equal to the concentration of the ions of the precipitate raised to the power of their coefficient once they're dissociated. We also have molar solubility, and molar solubility is the number of moles of any substance that can dissolve into a solution before it's a saturated solution. So until that solution is at equilibrium, because remember, a saturated solution is at equilibrium. The key to finding molar solubility from KSP begins with understanding our equilibrium expression. The KSP represents each of the ions of a compound at equilibrium when the solution is saturated. When we have a situation like this, I'm going to go back to a rice table for a moment to show you how we would come to this conclusion. Within a rice table, we're going to go ahead and assume we start with only the solid of the precipitate of that compound. And what we're going to do is start with 0 of the ions. Okay? So let's just assume we put this compound into water as a solid. Some of it's going to dissolve. How much? We're going to use S as a stand-in for X as our change here in solubility. And the reason we're going to use S is because S represents molar solubility. So when we increase the value of our ions by S or 2S, what we're really showing is S being the molar solubility, and 2S would be the molar solubility times 2. So at equilibrium, in a ionic compound that has 2 ions, like AgCl, what we would see is our equilibrium values being S for the Ag plus and S for the Cl minus. If I then look at my equilibrium expression for AgCl of Ag plus times Cl minus, what I would then do is plug in the S values into those expressions because of the fact that I know that the value of S is equal to the concentration of those 2 ions at equilibrium. This means that the KSP would equal S squared, or S times S. Let's take a look at one where the ions aren't 1-to-1. In magnesium hydroxide, when it dissociates into 1 Mg2 plus ion and 2 hydroxide ions. So if we write our equilibrium expression, Mg2 plus times OH minus squared is equal to our KSP, and we do a rice table, what we find is that the concentration of hydroxide at equilibrium is equal to 2S. That means when we plug in our equilibrium values, we find that KSP is equal to S times 2S squared. In order to solve for S, and this is really important, you need to keep in mind that 2S squared, where the 2S is in those brackets, we have to distribute that exponent. So what it actually becomes is 4 times S squared. That then multiplies by the S of the magnesium, and we end up with a total KSP is equal to 4S cubed. Now, the thing about KSP expressions here is that as long as we start with 0 as the concentration for each of the ions, we can actually kind of set up a standard rule for each of these equilibrium expressions. So in any ionic compound that has 2 ions, we know that KSP is going to equal S squared. In any compound that has 3 ions, whether it's 2 cations and 1 anion or 2 anions and 1 cation, it's always going to equal 4S cubed. If there are 4 ions, whether it's 1 cation and 3 anions or 3 cations and 1 anion, it's always going to equal 27S to the 4th. And for any time where it's 5 ions, So maybe it's 2 cations and 3 anions, or 3 anions and or 3 cations and 2 anions. We know that we're in a situation where it's going to be 108 s to the 5th. Let's go ahead and do an example where we find the molar solubility of lead 2 chloride. The KSP of lead 2 chloride is 1.6 times 10 to the negative 5th. Go ahead and, with me, find the molar solubility. The first thing we need to do is write our equilibrium expression. And the equilibrium expression of lead 2 chloride is KSP is equal to the concentration of lead 2 plus times the concentration of Cl minus squared. If we substitute in from a Rice table, what we find is that the concentration of lead would equal S, and the concentration of the chloride ions would equal 2S. We solve for S, which means that it's going to be KSP is equal to 4S cubed. We take the cubed root of our KSP and divide it by 4, and we get 1.6 times 10 to the negative 2nd moles per liter. Here's a second problem, and it's going to require a little bit more complex math, but in the end, it is the same basic process. We have a KSP here for my compound, calcium phosphate, that is 1.2 times 10 to the negative 29th. I'm going to use a Rice table to be able to solve for my molar solubilities. So if I plug in my equilibrium expression, KSP is equal to concentration of calcium times the concentration of phosphate, calcium raised to the 3rd power, phosphate raised to the 2nd power. We're going to plug in the values for my Rice table. For the calcium, it's going to be 3S. For the phosphate, it's going to be 2S. And we end up getting 108S to the 5th is equal to my KSP. So I take my KSP, I raise it to the 1/5 power, all right, which is the same thing as rooting it to the 5th, to raise it to the 1/5 power, and then divide by 108. And what I end up with is 6.4 times 10 to the negative 7th moles per liter. So that's the molar solubility of my calcium phosphate. So that wraps up today's video. Let's quickly recap. Today we learned how to use the KSP expression to find molar solubilities of compounds, assuming we started with no ions of either of those compounds in the solution. As we continue through this unit, we'll talk about when there is an ion already in the solution, and we'll also go a little bit further in terms of what these different KSPs and molar solubilities really mean. Today's video was written, directed, produced, and edited by Elias Mukdisi and James Zhang. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.